Good day, everyone. I'm Bob Ackerman, the editor-in-chief of Signal Magazine, and I'd like to welcome you to our Signal Media webinar titled IP 101, Network Foundations for Secure Next-Gen Architectures. In today's webinar, which is sponsored by PAYSA, an expert will lift the veil on the underlying elements of the Internet protocol for greater understanding of IP functions and security. This presentation has been approved by CompTIA for one continuing education unit. Now, those of you who are familiar with Signal's webinars know all about our audience interface. Throughout the presentation, webinar attendees are encouraged to submit questions electronically through the Ask a Question box on the webinar console. When our expert is finished with his presentation, he'll answer as many questions as time permits during this hour-long session. Today's presenter is Scott Barella, CTO of PAYSA. Having been involved in the broadcast industry for nearly 45 years, Scott has a strong background in broadcast systems design and architecture, systems integration, and operations, especially with IP video. He also served as the deputy chairman of the technical working group of the Alliance for IP Media Solutions. So with that, I'd like to turn the presentation over to Scott Barella. Scott?
Thank you very much, Bob. Today's webinar is for those of you who were afraid to ask about things in regard to IP. And I've created this deck for those that wanted a little bit more understanding. And for those of you who do have a great understanding, you'll find some of the explanations and so forth to be interesting. Now, the evolution of video and audio over IP has come a long way. We started with analog signals in the yesteryear. I grew up with those analog signals and saw them digitized into some of the signals you see today in baseband video, but now we've moved them over to the IP. So it's not necessarily a new thing, it's just an evolution. And as a result of that, we're discovering some interesting things about it. But today, we're going to cover the basics. And I do mean basics. The Ethernet basics start with an IP address. Now, this address is similar to a street address. If we're going to have lots of participants in a network, we all have to have a unique address. And as a result, we have to be compliant to the standards that Ethernet comes underneath. As that, we have a subnet. And again, these are all similar to streets. Here's a subnet example. A 6940 North Jensen Street is obviously an address for a house, but in an IP metric using IP version 4, we use these octets. The 192.168.1.10 is the first address, the second one is .11, and the first one being the 3 octets in the Maple Street, and the other one might be a different street. For example, these are all different houses. House address number 10 and house address number 11 and 12 and so forth. Now, the way this is constructed is using groups of 8. We call them octets, and they're grouped together in 4 positions, hence the term IP version 4, 4 positions, 4 octets. Each octet starts with 0 and goes all the way to 255. Now, the position, actually 254 for those of you who are double checking me on this. Positions 1 is kind of the first one. If we double it, we get to 2. If we double that, we get to 4. If we double that, we get to 8. If we double it again, we can get all the way to 128. And if we add them all together, we have 256 total positions. For those of you curious about IP version 6, which is the next generation coming around the corner, they use a whole different system in not octal, but they use hexadecimal. And so we have a lot more number combinations. The subnet ranges are basically categorized as public or private. Most of the implementations of IP happens behind the public internet or a private range. And we reserve certain IP addresses to exist behind the internet or behind in private circles. That way these numbers can be used over and over and over again, depending on the enclave that you want to put them in. A Class C range is usually in the 192.168.00 all the way to 255.255. Class B starts with 172.16, ends at 31. It is a kind of an oddball one, but it does actually have a larger address range than Class C. And then, of course, Class A has a huge range from 10.000 all the way to 10.255.255.255. We call that a Class A private subnet. The NETMASK is kind of how we would take each of those groupings of 256 and bust them up or expand them or combine them. In the Class C range, we use a subnet mask of 255 3 times and then 0. Class B, 255 twice, 2 zeros. And in Class A range, we use 255 and 3 zeros. We're lazy people, us IP guys, and so we created abbreviations for this. Instead of typing out 255 3 times and a 0, we like to just use /24. These are all found if you have an easy access to the internet and can download an IP calculator of your choice. This one here is one of my favorites. It's BitCricket, and it can help you find the abbreviations as well as how you could split up the subnet, so that if you only wanted to use a portion of that, you would use the 255, 255, 255.128. And if you wanted to add more, add another octet next to it, you would use the /23 version. These are all kind of ways that we can have a number of addresses that we're going to use for our street. And then we're going to connect these streets together, and we're going to have multiple houses, coming back to our original analogy. As I had said earlier, IPv6 is the next gen, and as you may have heard, we've run out of IPv4 addresses publicly. So we're moving into this IPv6 space, and with it comes 340 undecillion possibilities. So I don't even know that number, but now you do. They're all done with headers. This gives the receiving party or the sending party some information they have to adhere to, and these packet headers are kind of easy to discern and quickly discern lots of information about the origination of the address and the source address and the payload length and so forth, all things that are necessary for the decoder and the encoder to explain to each other. So there's some extra information along with those pieces and parts. They're generally speaking busted up into two pieces: a wide area network, which is a WAN, and a local area network, which is a LAN. The virtual LAN does that within the context of a physical piece, but we can bust it up into several. It's akin to having a hard drive with two partitions. So you might have a hard drive in the DOS days with a C partition and a D partition, even though it's the same physical drive. And that's the same sort of thinking behind the VLAN, where we have a layer 2 arrangement. We have a physical space to actually traverse traffic information too. In the subnet part of it, we would use a layer 3, and we'll get to that in just a bit here. The local area network is kind of the basic. This is really combined of typically 1 or 2 subnets. They're usually confined by a physical a floor or a building. At my house, for example, you might, like others, may have a common 192.168 topology where you have all of your devices and addresses under one subnet and one local area network. If you had a building that, for example, had a floor of accountants, all those accountants might be in a typical single LAN where all of the workers that are using computers in that floor would be connected to that particular local area network. In a wide area network, there are typically several subnets, so that we can usually connect the physical subnet sites, such as cities rather, and campus buildings. So we might have a science building that uses one particular subnet. We might have a chemistry building across campus that is using another subnet, and we can combine those two so that we can talk to each other using this construct in what we call a wide area network. The virtual LAN is a little bit tricky, but the way I like to think of it is that in the old days, we used to have a switch for one LAN and then a switch for another LAN. And then we found a clever way of using just one switch, connecting everything to it, partition the switch in half, and I would have one switch dealing with one VLAN, in this example, VLAN 2, for example, and the other one being VLAN 5. In this manner, I use one physical switch, and even though I'm showing two switches here, I can combine the two switches and create two partitions in two VLANs. This helps us organize our traffic and organize our communications between the computers that are shared on the network. A lot of people ask me, what's a ping? This one actually comes from the IGMP, the Internet Control Message Protocol. I'm using a little example here, a very easy example of pinging. Now, the way you think about this is it's like knocking on a door. You want to know if anybody's home. And if somebody answers the door, you know they are. And if somebody yells behind there, they say, yeah, I'm here. What do you need? Then you announce yourself and you can start to communicate. So a lot of engineers will use this command over and again to make sure that the connection that they were about to embark on is in fact a connection. Knock, knock, are you there? And I get a response of 32 bytes. The time is really quick, 1 millisecond. Incidentally, there isn't really anything shown in this protocol, anything less than a millisecond, so I know it's fairly quick. And the time length piece is 64. That means in 64 times or 64 jumps from one connection to another, I still get a very quick response and in somebody's home. If, on the other hand, I have an address that isn't going to be on the network. In this case, I picked on 192.168.1.23. You'll see the response is destination host unreachable, nobody home. Knocking on the door reveals nothing. So those are the two pieces that we use very commonly. I'm asked about this from time to time. This is probably the most used command on the command line interface that I can think of. Let's get into what we call a gateway. Typically in our network, we choose one address that serves as a door between one set of streets and another set of streets. So I can use that gateway to traverse between the two streets. And I usually choose the first number in the octet. So usually .1s are, generally speaking, gateways. They don't have to be, but they generally are. This could be your router out to the output of the network for your connection to the internet. This gateway serves access to the internet service provider, and that gateway allows you to search and to surf the internet. When we allow alleyways and doors to other subnets, we can create many of these gateways. So this is really the foundation of how we do routes. There are various protocols, one of them which was ping, and the other one in that internet control messaging protocol, IGMP, is a thing called traceroute or tracer. This traceroute is wanting to know what's the path from me to, say, a common internet address. So, for example, my old Hans at CBS, I could say tracertcbs.com, and it would search its address and show you all the links between your home and to the actual site that cbs.com hosts. And it will allow you to see all the links in between. There are other pieces and parts of the protocol that you can investigate. They're all underneath the IGMP piece. The internet protocol is unique. This is different than, say, sonnets or some of the other pieces, but this one is very common these days, and this is how we traverse the internet, for example, because this is where it came from. It establishes the addressing scheme that we use in most IP usage. With it come other protocols like TCP and UDP and RTP, and these I'll get into in just a second, but these are common protocols underneath IP. So we have basically three tiers. an application tier, transport tier, an internet tier, and a link, a physical way to speak in electric terms. So we have a few questions for you.
Okay, everyone, we're going to conduct a poll. This is where you can take part in this presentation. The question is pretty straightforward. Which of these presents a known security risk? TCP, UDP, gateway, SNMP, RTP, ICMP, or NETMASK? So, if you'll please pick what applies, respond, and in a short while, we'll come up with the poll results. In the meantime, Scott, how do you see, over the many years you've been involved, how do you see the internet changing in terms of stresses and strains on it?
Well, there are many. The first one we actually brushed on in the IPv4 format. We've run out of space. We don't have any more numbers left. So there was big concern a number of years ago, and we've been very resourceful over those amount of years. And so one of the answers to your question is that we are going to have to change the way we actually address ourselves. And so that's the next generation known as IPv6. It really isn't quite common yet, but I am seeing it. I've seen it from my cable modem, for example. When I look at my cable modem, it has given me, instead of a IPv4 address, it has instead given me an IPv6 address. So we're starting to see some of those changes. The other parts of the stress is just the sheer volume and all of the bad guys and good guys that are on it. We don't have a really easy way to discern that. So we have to be very careful about how we're implementing structures that do hint the internet.
I'll have to check my router next time. In the meantime, let's look at the poll results. It appears that gateway is slightly ahead of SNMP as the topmost security risk for people. I guess TCP is next, followed by UDP, RTP, ICMP, and then NETMASK. Okay.
Yep.
What are your thoughts on that? Are you surprised by any of those findings?
Not at all. Not at all. In fact, you might be surprised to learn that all of these are actually security risks, depending on how they're implemented. But the most glaring one is the one that at most of the listeners here today have guessed correctly, and that is, of course, the Simple Network Messaging Protocol, SNMP. That one's a huge security risk these days. The reason why is that in its infancy of learning about objects on the network, we were interested in if anybody was having troubles. And so we were thinking of a simple method of using internet addresses that we could use to alarm our system in a manner in which we could find out, gee, is the server having troubles? If the router acting up, is a wiring hub having problems? And this is a way that early on in networks, managers were able to implement a simple method to gather information from objects that were not a part of the actual communication. In other words, kind of the behind the scenes, gee, are you feeling okay today? No, I'm not. I'm actually a little stressed out because I'm having to put out more packets than I thought I'd have to put out. Unfortunately, because they use IP addresses, they become very, very easy targets for bad guys to mess with the network because they're so easily to grab hold of. And so even though it's gone through several versions, version 1, version 2, and finally the last version was version 3, which hasn't really been modified since 2003, this protocol has kind of disappeared. And we don't really see it that often, but it is kind of been dismissed as a security risk. But it was used early on with the noble hope of finding out information about the network. So with that, there are several different kinds of way we can traverse the network. We can actually create unicast traffic, and this one's really easy to see. We take a sender, and we have a listener or a receiver, and we connect the two. And in this manner, we have a one-to-one relationship. It's not so easy when we do it in a broadcast or in a multicast because we have to speak to several. An example of a broadcast sender might be the use of the NTP protocol, the network time protocol, where all receivers need to know what time it is. And so the sender, the server in this case, the NTP server, would send out various messages to the receiver when requested for checking its time, so forth. Multicast is a little bit more aimed so that I could just select certain receivers to send to, but the idea is I could choose multiple. I could choose all, several, or just one. So we have a lot more variability to the idea of sending traffic from a sender to a receiver, hence the term multicast. The unicast, as I had mentioned, is a one-to-one relationship. In this case, it's a very simple example. I have an IP address in version 4 from the sender at .10, and I have the receiver setting at 11. Once those two are made, those are the only two talking. This is very rudimentary and very simple messaging. Multicast can talk to several. So I have a source port, but because I have a single address, I need another mechanism to declare so that other people can use that same address to connect to. So if I use my IP address, I'm back to unicast. I can't stop the transmission and then connect to another. So we use what we call a multicast address scheme. And there are certain numbers in the octets in the version 4 protocol that we've reserved and set aside. And they actually start at 224 and they go all the way up to 230 something. But 239.1.1.1 10,000 is a common example for a particular multicast address, but its source port is emitting from a particular address. In this case, 192.168.1.10. So in the early days, when I saw interfaces from video equipment manufacturers, they would say IP address, and they would make you enter either its source port or its multicast address. And so for abbreviation, they would put 239.111 and your port address. It was a little deceiving in the sense that it made the idea that that was in fact its IP address, and that's not true. It is still 192.168.1.10, but it's going to emit a multicast transmission over 239.111 port 10,000. So in this fashion, the receiver can listen to that multicast address even though they have different addresses within the subnet. In this case, I've picked out receivers 2 and 3, which are addresses 12 and 13, that are listening to 239.111 10,000. Multicast uses another address, but it uses the IP address of the source port. And this is the key thing to take away here. A lot of folks get this mixed up and think that the multicast address is the IP address. In fact, there are two pieces here. The Internet Group Message Management Protocol. I love this little slide with all the meerkats. We use this guy to be the joiner. And these little meerkats are looking out for who's going to want to talk and who's going to want to listen. So the Ethernet switch under version 2 is fairly basic. In version 3, it's a little bit more evolved and a little bit more sophisticated and a little bit more secure, actually a lot more secure. The joiner is actually listening for a request for a multicast emission. So the thinking behind this is that if I don't have a listener, then there's no reason for the traffic to exist. In other words, I have a transmitter, yes, but if he's not having any audience, there's no point in putting his traffic on the internet or into the switch. So it's blocked off. When the listener is asking the switch, hey, I want to listen to this address, and the switch says, I have that address, I will join you two together. It uses this protocol to join the two together. In this fashion, the next person who wants to join that same transmission, in the case that I'd used before, 239.111.10,000, the requester comes from that and says, do you have that emission? And the switch says, yes, I do. Let me join you. It's very, very simple, very straightforward. Now, it has to happen on layer 2. That's the trick question there. It doesn't happen in layer 3 schemes. And I'll get into that in just a bit. The source won't connect without a listener. This is the idea. So if you've ever been to a party where you've had one person at the party be very chatty and nobody wants to listen to this person, wouldn't it be nice to take some duct tape and put it over his mouth because nobody's listening to this person? This is the idea behind IGMP. And in fact, the source will not be involved in any traffic that it's emitting from its port unless it has a listener. So when we have an audience for the listen traffic, then we connect it. And when we don't, we leave it be. If you don't have the IGMP snooping feature turned on to the switch, what you will do is you will flood the network. That means that that address is going to every port, to every listener, whether he wants to hear it or not, and that causes problems, especially with video, because the video payloads are very large. So this method is extremely important to keep in mind with, because we don't want to interrupt the entire network with miscellaneous traffic that we don't want to hook together. Now, with video, especially with video, we have to be very concerned about Ethernet pipe sizes. And one of the big reasons why we really haven't seen the transition from baseband signals like SDI, which is serial digital interfaces, or HDMI, you may have heard of that one, or DVI or VGA, all of those kinds of things require a fair amount of bandwidth. And we've kept them kind of cordoned off from the network, mainly because the network didn't have the kind of payload that we could actually switch with. Here only recently have we had 10 gig networks and 1 gig networks and the use of compression to actually pull this off. But I wanted to bring to mind here that Ethernet comes in various pipe sizes. At the beginning, there were actually some smaller versions than 10 meg, but we'll consider that the beginning for most. In fact, I see very little reference of that anymore. It's now all combined together in 10, 100, and 1000. But fast Ethernet was considered the 1 meg payloads. Gigabit Ethernet was 1 gig, obviously, 10G for 10 gigabit, 25G for the newer things, and 100G, 400G, and there's even talk now of 800G. So these all come in various pipe sizes, and these are kind of the standards that we use within Ethernet to traverse payloads across a switch or a network. When we talk about video, we have to go back to the roots of where it started from. So when we talk about baseband video, we talk about its uncompressed versions of it. So in standard definition 4x3, we started out with payloads at 270 megabits, and we could use 1 gig Ethernet ports to do that. But when we get into HDSDI or HD signals, this would be 1080i or 1080p, we're talking about much larger payloads. These would require 10G and higher Ethernet ports. And so these were one of the reasons why we didn't use these in the beginning. We did, in fact, use a lot of compression to move some of these video signals around a network. Now, Ethernet is based on packets. Packets are emitted onto the network, and packets have to obey very, very strict rules. And that's because we have a very unique standard in Ethernet that obeys one primary systems interconnection model. That is known as the Open Systems Interconnection model. Some refer to it as the OSI stack. The stack starts from the physical layer at the bottom and traverses all the way to the top to the application. This is still used to this very day. Why? Because this is the standard on how we do that. Now, if a lot of this is very, very loaded with acronyms and all sorts of extra letters and so forth. But for video, we can break it down into much simpler methods, and we'll get into that in a bit. The phi level, or the physical level, is where we have ones and zeros, or the electrical emission or the optic being a copy of that in actual physical signals or light. These are physical properties. Once we get past that, we get into the actual network standard. And there were several to choose from, but the one that we're going to focus on today is the Ethernet standard. The Internet Protocol, which is IP, is a protocol within the construct of the OZ, but it's not the only one. There are several, but we're going to stick to the IP side. The Universal Data Protocol, the UDP protocol. This one is how the packet is actually, or one of the types of packets we can use. And another type of packet we can use is the real-time protocol packet. Now, this is the stack kind of broken down. And you can see in the bottom here, we're talking about physical transports. We don't talk about things like DSL, or we don't talk about T1, E1, or ATM, or any of these older ones. We're sticking with, in fact, Ethernet. The next pieces up are what we just talked about, ICMP, ARP, DHCP, and one of which is the IP. The next one is TCP and UDP in the transport segments. And then there's POP, DNS, HTTP, and it gets wild from here on out because there's lots of them, right? But for today, we're going to make it very simple. The only ones we really need to focus on are the PHY, the Ethernet, the IP, UDP, and the RTP. This part is the studio video over IP. This is the part that we were really concerned with when we wanted to start moving video around a Ethernet network. Now, is it a router or a switch? This is always a good one. In the early days, they were separate devices, and in today's format, they're built in together. So one man's switch is another man's router. Depends on how you want to use the device. Switches primarily work in layer 2, although that's not necessarily always true. But the routers, generally speaking, like to use layer 3. Why? It's easier to construct. The router switch is a basic LAN-based switch, and it can route around at L3. The IP router does more than just route. It typically uses WAN applications, and it can support things like IPsec and all these other type of other non-Ethernet protocols as well. But we'll stick to some easy pieces here. Layer 3 is the network layer of the OZ model, and it's the logical addressing in IP addressing. So imagine if you could take a flow and actually tag it with an IP address, apart from the objects that are on the network. So you have to be very careful about the addresses we choose, because these addresses are known to all the models that are out there. So usually these are confined within just the switch. In the layer 2 side of thing, we actually use the physical addressing, or the machine address code, or MAC. Most are surprised to learn that when we connect the multicast, we do that at layer 2. And in layer 2, when we connect the two streams together, we actually don't care about the IP address. We actually connect the MAC addresses, the physical device to the physical device. Why? It's easier to do on the layer 2 side of the switch. Now, here's a basic kind of a construct of a network topology. We have a core switch. We have the end of rack switch. We have a top of the rack switch, and then we might have some servers underneath it. This kind of topology defines our network in an aggregated sense, and that all of this is our network, so to speak. In the RTP packet, I'm going to jump around just a bit. The real-time protocol helps us with video tremendously. In fact, without this guy, it makes video extremely difficult and challenging. But we ended up with two very unique pieces in here. First of all, some people are surprised to learn that the RTP packets aren't emitted as RTP packets. They actually have to be bundled together in a wrapper of UDP. The Universal Data Protocol really doesn't care what goes into it. So we can actually put real-time packets within the UDP packets. We can only stuff in a normal UDP frame of 1350 MTU. We can only fit about 7 of them in there. with having a little bit of breathing room for all 7 to coexist. And we want to sequence them. And so you'll notice in the header, we have a sequencing of 1, 2, 3, 4, 5, and this goes ad nauseum to a very high number, and we start again, so that when we try to reconstruct these packets, we want to put them back in the proper order. Why is that important? Well, it's important because if we're trying to put a frame of video together, we want to make sure the video lines go together. And so this is extremely important. The other element is that large number you see on the bottom, and you'll notice it's incrementing a higher number as you traversed from left to right. Those are the PTP time packet stamps. So we get 2 pieces out of the RTP packet. We get a sequence number and we get a time code stamp. That's pretty handy when we want to know when that video happened and the order of that video as we try to put it all back together at the decode end. And we want to start this from the encode end. Here's a breakdown of that. Remember, we had packets in the actual parts of other pieces and parts. In the RTP packet's kind of interesting because you'll see a place for the sequence number just above the timestamp, which I've highlighted in yellow. This is really good because we can use this timestamp. One of the challenges that we had with video is that video is constructed on a frames per second basis, and they didn't work within the context of tenths, hundredths, thousands, millions, or increments of 10-based math like we have with normal time. So we have 10.2 seconds, for example. In video, we have to break our frames up into the time standard. The Society of Motion Picture and Television Engineers came up with a standard called 2059-1 and 2. And this was a method to use PTP time alignment so that you could have a proper timestamp. And when you wanted to decode it, you could actually figure out what it meant in terms of real time. And so that large number that you saw before is actually decoded to the actual time of day and so forth. So this is quite handy for video. When we talk about flows, in the old days, we had an embedded source, and then we took all of the things that went with it. And when we started to work with this in compression, we started to take the video and the audio and the data, and we moved them all together. What we found was that if we divided them up into separate flows, we could actually manipulate them better. So what we wanted to do was arrive at some scheme of taking flows, whether they be USB signals or video signals like HDMI and audio signals. We could actually create flows for each of those. So the video would have a multicast address that's unique, and the audio that went with it as a unique address as well, and the USB as a unicast connection. Why is that important? Well, one of the advantages we have with this is that we can actually switch video separately from audio. So if we want to keep the video and we just want to switch the audio, we could have the access to the address of just changing the audio and not affecting the video. Same thing with the USB. We might prefer to have another connection with the USB. Note that there's just one network interface. So now we can combine several different signals where we used to have different wires and different types of wires like coax and twisted pair. We can now use one common interface in IP. The same thing is true on the other end, so that as the decoder receives these traffic signals from one interface, I can derive several videos or several audios or several USBs to choose from, and then I can decrypt and decode and de-encapsulate those as I wish. Now, the network IP matrix is a lot different than the baseband address. One of the advantages is scalability. We end up with near limitless sources and destinations, but the thing to keep in mind for video and audio is that we have to have a non-blocking architecture. That's slightly different than office architectures, where we can have a little bit of a blockage. In other words, if you're looking at a particular thing on the internet and it's a little slow, that everybody is busy on the network, we don't really mind so much. But in video, it would be interrupted. And so that's not an architecture we would probably prefer to use if we wanted a full stream and everybody needed an unblocked view of their signals for video or audio, whatever. If they would be interrupted if we didn't use a non-blocking architecture. And as far as scalability, we would have to incorporate some leafs and spines and ways to incorporate all of that. So we do end up with some really interesting architecture addresses and some advantage of it. But as it exists for government, we run into a thing called the Federal Information Processing Standard. This FIPS piece is kind of key to security. The switch basics for ports come back to its physical levels. There's two basic types, copper and fiber. On the copper side, this is really a rapidly evolving area. I would have never guessed several years ago that we would be able to use 10 gigabits in copper, but you're seeing it now. There are standards now that are addressing 10 gigabit Ethernet transmission over copper methodologies. Now, they don't go very far because it does have that limitation, but it is interesting to see these topologies come alive these recent years over common RJ45 ports that support them. The fiber side has been going from some time. It started with the SFP beginning at 1 gig or so. It has traversed itself all the way to SFP28s, which go well beyond 400 gig and can be busted out in quad groups. But there are basically two types of Ethernet traverses and all sorts of sizes that go with them for either electric signals or fiber optic signals. The switch bandwidth is interesting because we have a number of ports that we can collect on a particular switch, and we use a backplane in the switch to aggregate all of those payloads and then move them around to make the connections from either switch to switch or port to port. The backplane is generally very, very high, and generally speaking, it goes on the nature of about 10 times higher than all of the ports aggregated. So if you add all the ports up at whatever payload they're listed at, the backplane is generally at least 10 times higher than it is, including all of the uplink ports. So a lot of people wonder if there's enough space for uncompressed video or slightly compressed video or highly compressed video to move around on switches. So the answer is yes. But it also comes to the idea of bandwidth, right? So in a bandwidth, this is how many cars, for example, we could get in a particular second versus the throughput of what we would normally expect to get through a particular pipe. You've all been in a traffic jam, and it depends on whether traffic is good that day or traffic is bad that day. When you aggregate a lot more traffic, the traffic throughput gets a little slower. When it's fast, you have a little bit more space in between the cars. So this is kind of the same thing true on electric signals on a particular switch. Now remember that the Ethernet is bidirectional. This is the input and output being on the same port. This is also known as ingress. Ingress equals input, and egress means output. I'm not sure who came up with these. Transmit and receive is where it started from in twisted pairs. This happened even before Ethernet. This was common in RS-232 and some of the early serial protocols. But there was a twisted pair and a twisted pair for receive. And as we went even through fast Ethernet, there were really only 4 cables or 4 wires that were actually used. As we invented gigabit Ethernet, we just added more pairs and so forth and so on. In fiber, we actually get to use a lambda or a light frequency, and it does the same thing. But you'll note that there is a transmitter to the left and a receiver to the right. So when we talk about a port, especially with unidirectional type signals, which audio and video tend to be that way, we still have a bidirectional port that deals with it. We may not use all of the half of the port as much as we do the other, but they are still there, and we have to be cognizant of how that Ethernet is worked with respect to input and output payload. Here's a very simple diagram of how an interface would deal with an egress flow and an ingress flow. There's a paper at UCSE EDU. This was published by Arista, and you can follow that link on that for further discussion. This is a whole paper, but to give you some notion of it, the interface comes in, it's parsed. It's L2 is looked up for its MAC address. The L3, if it's there, is checked against the host. And then the egress, the access control list is checked to see who's available and who it's supposed to be connected to. So there's all these protocols in between that are checked within the switch. The packets are then sent out almost in the same fashion, except that it's much more straightforward on the egress side than it is on the ingress side. A very simple broadcast system I've chosen here to illustrate 5 devices, excuse me, on left, and 4 receivers, 5 transmitters on the left, and 4 receivers on the right. I started with device 1, 2, 3, 4, and 5 to the left, and I have 6, 7, 8, 9, and 10 on the right. Now, you'll note the transmitters have the multicast address, but the receivers do not. That's because the receivers don't emit. They only receive, so they have to only call out which ones they want. And that's a very simple example of how a box that might have a transmission property and it's emitting on a particular address at a particular multicast address, and how the receiver would traverse through the switch and then pick that up as directed. One thing that comes to mind when you start to grab more switches and you start to aggregate this and you grow and scale this network to more and more nodes, you end up with usually these type of architectures. We call them spine and leaf-based fabric design. Now, where the fabric came from is this altogether. So when people refer to network fabric or switch fabric or Ethernet fabric, they're actually referring to a combination of all of these switches being compressed into one handy way of saying we've got this fabric that has different payloads and we're going to move them around from point A to point B. When we do that, we have a lot of traffic to take care of. And one of the handy things that we're using in the media side of things is a thing called software-defined networking. And when we get into these designs, it's required to keep track of all those uplink ports that you see the arrows connecting the switches to. We have to keep track of how much payload is going to each switch from each switch. And the backplanes on each of those switches can take care of what it comes in and what it goes out. In other words, the switches are perfectly designed to handle a maximum amount of ingress and egress, but we have to have some methodologies with respect to connecting switches to one another. This allows this non-blocking architecture that is so very important in media networking. First, we have to start with a method of being able to see what we have on the network in terms of what it is we have. Do we have senders? Do we have listeners? We need a method to discover and register what we have. So when a particular node comes onto the network, we need to know whether it is a sender or a listener or both. And we need to be able to find out what properties that go with that sender or with that listener in much the same way that DHCP works, in the sense that we have a computer that we need to connect to the network. It needs an address to talk to resources on the network. We want to go through some security to make sure that he's authorized to do that. And in the same vein, we do this with kind of the network side of things for media, and that we need to know whether it's a listener or a sender. Remember, the audio and video is pretty much unidirectional. We have a start and then we have a finish. We have a send and then we have a receive. So in this sense, we need to know which is which so that we can find out from the control how to do that. That's contained under the Network Media Open specifications. There are several that are out there today. We chose this one because the Society of Motion Picture and Television Engineers chose it as one of their preferred methods. It doesn't say that it's the only method. It just says that it's one of them. So I chose this one today to at least illustrate the point of being able to point out that there are unique requirements for media. And in this, we have a method to actually switch it with. And I'll get into that in just a bit. But the ISO 5 part of NMOS refers to the method of switching in a break before make. Why is that important? Imagine two sources at 1 gig and I have a 1 gig I'm going to connect it to. So for example, at source A, I have a connection to make in the X area here, where I'm going to say that's first one, and he's going to be 1 gig. And so I have to make sure that before I switch to B, I can make or break that connection. So in the make before break, I would have another source that would be the same size. So for a brief moment in time, I would have 2 sources at 1 gig. So a make before break would double the bandwidth before I actually commit to the switch. So in this example, I would have 1 gig at source A for a minute or for a brief frame, a packet. I would have both source A and source B, and then I would eliminate source A and I would switch to source B. And that's the point here. A break does this for us. So I would break source A before I connect to source B. Now we use the same bandwidth. If my port is only 1 gig, that's why this is important. I would have to have the knowledge that I can't have anything higher than 500 megabits, for example, because 500 megabytes times 1 would be the port capacity of the X switch port. So break before make is the method that we generally use in media. Before we get into the scaling, the scalability of this is such that we have virtual sizes and elastic growth, flexible architectures. But here's the most important thing to take away for today. FIPS 140-2 is alive and well in most government agencies. These are required for all IP communication. And that's where FIPS encryption is dictated. The Department of Defense's information network mandates that all IP use FIPS encryption. So these FIPS modules are certified by NIST. And as long as I use one, our company, PAYSA, used one, and we have a certified CMVP certified module. It doesn't mean that it has all the certs and keys and all that sort of thing. This is just the raw crypto of that. But it's important to note that all IP communications is required to have FIPS. A secure room kind of looks like this, where we have a number of assets on the floor, and we want to connect them. We have multiple independent levels in this particular enclave, and here we have an unclass, a class, a secret, a top secret. The move that we're seeing is all of these assets moving into a secure room. And in this sense, once we move all those assets, we now can move all of those assets to the floor as we dictate. So in this manner, we can make all the seats classified, we can make all the seats secret, we can make them any mix that we want, and dictate whose seat gets what. And that's really the construct of how IP video is secured into these enclaves. That obviously begs the idea of a single room enclave to a multiple enclave. There's all sorts of pieces and parts to this as IP scales. As it scales, the idea of virtual SCIFs comes to mind. A SCIF is a compartmentalized information facility, a sensitive compartmentalized information facility. These SCIFs are dictated and usually connected by the military, not by third-party vendor like myself, but they'll need a method to encrypt their communications backwards and forwards. And that's kind of the idea behind that. So how do they actually work? Well, we'll tell you next time when we have another great webinar, thanks to Signal Magazine. We'll be doing some more use cases in our next one.
Okay.
So here's the summary, and I know we're getting short on time, so I kind of glanced through this one, but here's the top rates, and I'll just go right straight to Q&A.
All right, Scott, thank you. Remember, folks, the Q&A should go to the Ask a Question box, not to Scott's email there. That's for afterwards. So, Scott, if you could go back to that previous slide, that might be better. I also want to do, thank you. I also want to do one housekeeping piece. Some folks have asked about the continuing education credits. Under the resources tab, there is a link that goes to CEU frequently asked questions. So if you want to know how to apply this webinar to your CEU, go to the resources tab here, and then that first link will take you to the facts, and hopefully you'll find the answers you need right there. But let's quickly dive into the questions. We already have some, The Ask a Question box is the key. First question, you commented that SNMP is not used much anymore. Cisco NetFlow and other network monitoring protocols, I believe, require SNMP v3. Is NetFlow not widely used?
I don't see it as much, but then again, I'm not speaking for every use case. So that's not to suggest that it isn't used anymore, but I do get, I can only tell you from past experience, our company actually operates a lot of the SCIF environments in our baseband products, and we were asked to take our SNMP protocol out for their use. So that's just, I did say that there were other protocols that would obviously be a security risk as well. That's not true of everything. It's not an across-the-board statement, but in general, I find less and less usage of SNMP in general.
Okay, well, our next question is about our friend SNMP. You mentioned SNMP was a security risk. It is used for control. How else can I control devices if I don't use SNMP?
Right, that's a great question. So there are more sophisticated protocols that are out there, SSH is being one, but there are also API calls that are encrypted and held safe so that you can glean the same information that you could from SNMP in just a slightly different manner. And a lot of the switch vendors and a lot of the equipment vendors that are coming online for secure environments are actually commenting on how all of this information from pieces and parts of the health of the network can be done securely. And so I would invite you to take a peek at some of the Cisco and the Arista type of models that they are actually creating information about these pieces and parts of the network and bringing them back safely with respect to not showing everything in it. This is kind of one of the reasons why it was considered one of the hacks that have been done here recently to some of the pieces and parts of particular networks. If you've been reading about this in the SolarWinds stuff. So,
okay. Well, the topic continues. Yet another question has just come in. Is DNP more secure than SNMP?
Some consider it to be, others don't. So there are other avenues to glean information from objects that you're trying to gather information from. Those are generally done via FIPS and the standards that they've created. So I would invite you to take a look at the FIPS standards as they relate to all sorts of different pieces and parts of the network.
Okay, next question is not on SNMP. What are the best diagnostic tools for AV/IP network problems?
One of the pieces and parts of media has to do with of jitter and some of the other pieces and parts of video that are particularly keen to. Remember, we don't have the luxury of a sync pulse when we use Ethernet structures, such that we put lines of information into packets, but we don't necessarily have the luxury of a vertical interval line to pulse it with. So jitter becomes an extremely important thing to video. Some of the tools that are out there are made by a number of third-party vendors. Perhaps offline, I'll recommend a few of them. In this public venue, I'll stick to just the idea that there are several tools out there that address these head-on, but I would say parenthetically that most of this revolves around the health of the actual signal. And the signal for media is the jitter spec. That tends to be one of the more important pieces for traversing video in a mezzanine or an uncompressed side of things. In compression, it's a little bit different in that we can gate that slightly different. But all the network tools that go into play for other things are just as important and have nothing to do with media. And those can obviously be very important tools as well. Okay,
then. Next question. How will IPv6 handle traffic prioritizing protocols like QNQ?
That's a great question. That one, I mean, we are just now seeing the use of IPv6, and a lot of it hasn't been figured out, frankly. I see very few pieces and parts that are being used, and it's mainly because the private address range was really well thought out, and that we can handle a lot of traffic on the IPv4 side privately. And the same is true in IPv6, but there are other tools and other obstacles and other complications that IPv6. It's not simply a matter of an address change. There is a lot more to IPv6. In fact, I would almost suggest there's an entire webinar just on that subject.
Okay, then. Yes, there is a lot to IPv6. Next question. In a SCIF environment, how much is physically isolated versus SDN configuration?
That's a good question. One of the problems that we see in SCIFs is the isolation of that SCIF for good reason, right? We want to keep all those signals inside of a physical architecture. And then when we need to connect that to something else via a network backbone or whatever, it gets dicey. So at its intrinsic level, the connection is a security risk. So most of them don't do this, or if they do, they clear the both enclaves and they wrap it up, and then they create one enclave, and they have a method and a procedure to do that. But it involves physical patching. One thing that doesn't exist is something that I hinted at in the first part of this, is that there's all the security that's required in IP has to be encrypted. So at its very nature, at the very beginning, the video and audio would have to be encrypted. So before I even connect SCIF 1 to SCIF 2, I would have to have those signals encrypted. Those are the pieces and parts that we're wrestling with, right? And those are the things that we're working on in development from our company. But the idea is that it is possible to connect securely to SCIFs, provided we follow the same outlines and requirements that those SCIFs require.
Okay. See if I can squeeze one more in here. How will the migration between IPv4 and IPv6 occur?
Carefully. Yeah, I have rarely seen mixed environments. It's usually an all for one and one for all. So I don't see a mix. Now, I have seen where a device can, obviously, your PC is a great example, where it can have both addresses and connect independently. But keeping track of all those in a network is a little bit different. The primary implementations that I have seen have been public, where you see a cable provider or a internet service provider work with public addresses in terms of IPv6. Usually that organization does one or the other. They don't usually do both, depending on the wide area network they're trying to serve. But it is difficult. As I alluded to earlier in the IPv6 discussion, it's not as simple as saying, here's an address for IPv6, here's a connection for IPv4. What do I want to connect with? It's not that simple. So I have generally seen publicly they switch over. So for example, Comcast is a great example. They have switched over to IPv6 publicly in my area, and that's how my cable modem is secured.
Okay. Well, we've run out of time. That concludes our Signal Media webinar for today. I want to thank Scott for his presentation, and thanks to all of you for joining us. Our presenter will try to respond directly by email to any unanswered questions in the queue. Now, you can link to the archived version of this webinar, along with previous Signal webinars, on the Signal Magazine website at www.afcea.org/signal/webinar. Thank you again, and have a good day.